Lastly, in example 3, we have a beam that is supporting a distributed load as shown below. Our distributed load is characterized as omega naught cosine pi x per 2L, where omega naught is a constant. We want to determine the equivalent load using integration, and we want to determine the location of said load, i.e. where we can apply this load as a singular point load. Now, to determine our equivalent concentrated load, we have to determine the area under a curve, i.e. we have to integrate our distributed load along the length. We can say W is equal to the integral from 0 to L of W dx, and this is equal to integral from 0 to L of omega naught cosine pi x per 2L. This is going to be equal to 2 omega naught L pi times sine pi x per 2 evaluated between 0 and L, which is equal to 2 omega naught L per pi times the quantity sine pi per 2 minus sine of 0, and this is equal to 2 omega naught L per pi. Thus, to determine x bar, we need to determine first our moment of area, i.e. the integral of x omega dx, and this is equal to the integral of 0 to L x cosine pi x per 2L dx, which is equal to 2 times the quantity pi minus 2 times L squared per pi squared. Now we can say x bar is equal to integral of x omega dx per the integral of omega dx, which is equal to 2 times the quantity pi minus 2 times L squared per pi squared per 2 omega naught L per pi. And we are left with pi minus 2 times L per pi omega naught.